Yeah, hi, my name is Nate, and this is Talk About the Future. And if there's one thing that's clear to me, it's that there's no real clear vision of what the future is. Everybody kind of has their own ideas of what it is or should look like. But if there's one person who said it best, Shakespeare described the future as the undiscovered country. And that's actually appropriate because countries are very big places and we have a lot of territory to cover. And I'm going to be moving kind of quickly because we only have about half an hour. So to sum up, that's it. You can go now. No, actually, this isn't really a talk about languages, although it is a talk somewhat about language. Primarily, though, it's a talk about ideas. And I've been trying to think of the best way to sum up this talk, and the best thing that I can come up with so far is a series of hand gestures, specifically and we spend most of our time as programmers kind of like thinking about things down here. And I want to invite you to just take a little journey with me up here. And when I say up here, that's not like an elitist thing. It doesn't have to do with like, title or job function or any of that stuff. It's more about the fact that we don't think critically enough, I don't think, about the work that we do as programmers and how we got where we are, as opposed to just sort of like solving the immediate problem. And I think this problem has become so pervasive that we've actually elevated these like little arcane technical details that we have to, be in front of every day into like a high art. And it's gotten really bad. We're kind of like hitting local maxima on the effectiveness of this approach. And like seriously, like it's cool that you can develop crazy fast muscle memory with Vim and all your plugins and everything. But Vim is a derivative of VI, and VI was invented in 1978. And from that day to this, our idea of what programming is has always just been, writing code in a symbolic language in a text editor. And that's just sort of one example. It's sort of obvious, it's always right in front of us, but our industry is littered with like these things that just go unnoticed and unquestioned that are rooted in technologies from the 1970s. And so I really think that in order to break out of this box, we need to be able to sort of think about programming abstractly in terms of first principles so that we can really move forward. I think part of the reason that we have this problem is that technology changes very quickly, but our minds change very slowly. Like it's hard to really adopt like a genuinely new concept, especially on a societal level. So that's why all our terminology and our metaphor is like, come from publishing and architecture and filing cabinets. And so we have to, it takes a lot of effort and a lot of hard thinking to kind of move past that into a new way of thinking where we can really own that way of thinking on its own terms, if that makes sense. So I do software architecture at a consulting firm called Ratify, and this is not merely shameless self-promotion, it's actually material to the story. I do architecture, and that basically means finding excuses not to write code while thinking about, difficult design problems. And I thought I was pretty good at it. I was the lead developer of Cake PHP for a while. I created the Lithium Li3 framework, which is, I felt like a little advanced for its time. I'm also the lead developer of Angular UI Router. How many people have used that? Just out of curiosity. Okay, a couple of you. So it's probably like in the top 5 libraries for AngularJS. So it's not nothing. But so I thought I kind of had this stuff all figured out. But regardless, there were kind of a number of things about programming that just felt wrong, like just little weird quirks and inefficiencies at like a fundamental level that just bothered me. So some time ago, I sort of created for myself the opportunity to take a little hiatus. I wanted to spend some time digging into like the history of computing, how we got to where we are, and kind of like why things are the way they are. And by the end, the overarching conclusion that I came to is that I have no idea what I'm doing. And that was sort of a depressing thought. I realized that basically everything that I had done in my career up to that point was not just useless, but in a way kind of worse than useless. And I mean, don't get me wrong, it was good in that, the things that I created, helped people do their jobs or, taught people things or whatever. And that's good, but I don't feel like I was really doing anything to move the industry forward. And in fact, just the opposite. I think my work has really helped to entrench and institutionalize some ideas that are holding us back. Now, in the best case scenario, my life is about a third over, and I don't know about y'all, but showing up and collecting a paycheck is just not good enough for me. It just doesn't cut it. So I couldn't just keep doing the same old thing. I had to figure this stuff out. There were a number of talks and one series of blog posts that I kind of kept coming back to, and these will all be linked elsewhere, and I'd really, really encourage you to check them out individually, but they were all from very different people talking about very different things. Yet at the same time, I couldn't help but feel like they were all sort of intrinsically connected in some way that I didn't quite understand yet. So the first thing that I decided to tackle, industry sacred cow number one, design patterns. The idea of design patterns has always kind of bothered me on this level that I couldn't quite articulate. But I found out that I actually wasn't alone in this. So Alan Kay, who you should all know of, kind of was dismissing this idea of programming patterns out of hand with allusions to some other concept of programming juxtaposed against the programming that we know today. And in his blog post, Beyond Design Patterns, Anthony Ferrara basically goes through all the common patterns that we use in PHP and basically reduces them all down to this one single responsibility of communication, or more specifically, modeling the flow of data through a system. But why in OO design does it require 22 different things to model the same responsibility? Why do quote unquote grown-up languages like Java have so many more patterns and things like that, and more structure than a language like PHP or particularly JavaScript, which has far fewer and simpler patterns? Why indeed? So story time. About a year and a half ago, I started working on a little tool. It looks kind of like this. It's a little hard to read, but you could sort of mouse over the things, and it showed you how classes and systems in an application were connected. And you could, mouse over the little edges of the graph, and it would show you the call traces that went back and forth. And I was using this as a tool to try and understand a code base that we had adopted from another development team. And the classes were reasonably well structured, but the system, it was just too hard to think about. And the original version of this graph looked an order of magnitude worse than this. I had to write a bunch of configuration to say, okay, omit these things, and take these classes and namespaces and group them into this thing called a database, then take these other things and group them into a thing called a queue. So it's cut way down from the actual version. But it was still really hard to tell what the meaningful connections were, because then you'd have classes that were in two different places at once and would be part of different systems in different contexts, and it just became really hard to disambiguate. And it just seemed harder than it should have been. Like the individual classes in the system were reasonably well organized, but overall the system was just kind of a mess. And an argument that I often hear is that TDD helps you with your design. And yes, I suppose that's true, but all the TDD in the world isn't going to save us from the fact that complex systems are very, very easy to create in our current conception of what programming is. Our tools set us up for failure because complexity is just the default. So inevitably, we sort of create a system that's more complex than we can easily understand. And so we end up in this sort of adversarial relationship with our own creations. And the weird thing is, though, that it just seems like that we're sort of fine with this. I would argue that as a programming community and a programming culture, there's no intrinsic incentive to want to improve this because the culture self-selects for complexity. We're all sort of comfortable with it. So just a few examples. of where this comes through. We'll start with everybody's favorite, mutable state. So 100 years before computers even existed, the top experts in the field had already identified that state was hard to reason about. In 100 years, things haven't really gotten any better. And I think this is a big part of why object-oriented design encourages us to hide little pieces of state all over the application. And we don't have, like currently there are no good tools that exist for observing state and how state changes across an entire application. There are no tools, but there are ways of designing things. So that gets into a little bit of what I want to talk about. But even the tools that we have for OO design don't really encourage us or point us in the right direction because they don't address this issue of state in a way that's helpful in the broad sense. Another thing that OO design does is it encourages boundaries that seem clean but actually aren't. Like, let's say you have one component and another component, and they need to talk to each other, and one maybe passes an object to another, and that object only has one dependency. But that dependency has this whole graph of objects that have built up state over the course of the request. So you're really not passing just that one object. It's not really a clean boundary because you don't know what else is going on, nested deeply within that tree, and you don't know how it's going to impact the rest of the system. And what happens when you have to move one of those components to a separate process or a separate machine? Are you going to serialize all that state? What if it has closures? It kind of breaks down. And a kind of a more esoteric example of this that has nothing to do with OO design but programming in general is that there's really no clean separation between the work that we do and the work that other people do that has to be incorporated in our work to present a final artifact. Have you ever presented a demo to somebody else in the company or a client, and it's really cool, you worked really hard on it, and they're like, that's great, can you just change that copy there? And you're like, you changed the freaking copy. I don't want to change the copy. That's not a good use of my time. It's like you can do the copy change, or you can glom on a content management system, and then you have to map between your thing, the content management thing, and it's just a mess. So there's no real good way of managing that. Let's talk about tools. So to start with, tool number 1, or number 0 rather, the CPU. The computer architecture that we have today was designed by a guy named John von Neumann. And it was basically a single channel between processor and RAM, and the processor executes one instruction at a time in a linear fashion. And this architecture was invented when RAM was a giant drum. So this guy is John Backus. If you guys know what a BNF is, he's the B. And he had a pretty scathing indictment of the von Neumann architecture. And he cited all these really, really serious deficiencies. And he's got a point. The von Neumann architecture has become so ingrained that what do we have to do to parallelize our software? We run a computer inside of a computer. We literally had to invent virtualization just to get real clean, isolated boundaries between our different processes. So then we parallelize them, and that's great, but how do they talk to each other? RPC? That would be the object-oriented thing to do. No, we send messages with data. It just seems so obvious to me that we all secretly want to be functional programmers, but our tools at the machine level just suck so bad. So Alan Kay actually had a lot to say about this as well. And so this is what it looks like when the machine and everything in our stack that sits on top of that is kind of working against us and working against our being able to do good design. But what about a different kind of environment where software can be more easily reasoned about? Alan Kay obviously worked at Park. They basically had a playground where they could kind of do whatever they wanted. But just the idea that they could create an operating system, a programming environment, a set of applications, and a UI layer in 10,000 lines of code, that just seems insane to me. And in the 1960s, no less. So that's the computer. Another kind of tool that I want to talk about is a tool that we also don't have. So this is my completely accurate, highly scientific graph involving the various disciplines involved in creating software. So you have this continuum of the mind where people like envision what it's going to be, and then you have this other domain on the other end called math and physics, or as I sometimes like to call it, hard realities. And so what's interesting about this is that programming is sort of like the original medium of thought, like in a way that something like writing and philosophy and music and art can't really be, because computers allow you to do simulation. And when you can, and that's like a really, really powerful thing. But there's this problem. These two domains have this really dichotomous relationship. Specifically, one is perfectly comfortable accepting ambiguities and contradictions, whereas the other one is not so much. So, I'm sure we've all had this conversation where it's like, somebody from the business or your client comes in and say, I have this great idea. We need to return API results in the shape of a unicorn. And then you have to explain to them, well, no, you can't return API results in the shape of a unicorn. People have to parse them. I mean, well, maybe, PHP 8, there's an open RFC on quantum superpositions. We'll see. But it's just, you can't do that. You can't reconcile that. And a lot of times you end up having to deliver these really esoteric explanations that don't make sense to domain experts who aren't necessarily software experts. So we don't have good tools for this kind of communication and this kind of reasoning. If the business wants something done, they have to send a programmer to go do it. Maybe the programmer comes and figures out that we can't do it for X, Y, and Z, and then you have to report that back. Well, that's a very long and expensive feedback cycle. And we also don't have just a tool for being able to sit down with a non-expert programmer and explore a system in a creative way just to figure out what's possible. We have very specific tools for that, but no general tools. So this is what a good tool looks like. And we've definitely got half of this equation down. We're super good at catering to computers, not so good about catering to humans. We don't really do tools that actually augment the way that the mind thinks about systems. And here's another somewhat related example. So let's say you're going to build a factory, and I think factories are actually way better analogies for software than architecture or whatever, because they actually have interconnected parts that do things. So let's say you have this factory, and you want to observe how it operates. Well, you just turn it on, right? Well, I mean, step one, if you're a programmer, is actually to cover everything up and turn all the lights off. And then, maybe we'll stick a thing in here where it's like, okay, we'll look at this one part of the thing, and we'll call that logging. That's a log entry. And then we'll have another log entry maybe somewhere else, and so on. You get the gist. But maybe if you want to step through, debug the factory, maybe that'll look something like this. It's a problem. It's a problem. Our systems that we create are by default not observable. And if we already have a hard enough time thinking about things that are dynamic, that seems like pretty bad news. So I was starting to feel kind of down about all this stuff until I discovered this quote from Kent Beck, who unwittingly saved me. He gave me a frame of reference to think effectively about all these different problems. So we're going to keep coming back to this. Anyway, the first kind of place where I felt like this principle, like I was violating this principle, was actually frameworks. And I just begun to have this sneaking suspicion that frameworks tightly couple things that don't belong together. Specifically, they couple a set of components and a set of design decisions. Well, if the components are good, they should work independently on their own, independent of the design decisions, and vice versa with the design decisions. Now, there are frameworks that claim to do this. There's only one I know that actually does it because of the aforementioned object-oriented dragging around of a lot of baggage problem. We're not going to get into that because I don't want to name names. That's rude. So this gets back to the idea about breaking out parts of the system that do the work from the parts that compose how the work is done. In Gary Bernhardt's talk, Boundaries, he refers to this idea as separating arrangement from work. And actually, he gave this particular technique a name. And by looking at a bunch of different emerging architectures, he kind of distilled it down into this idea that he calls functional core imperative shell, or OO, or sorry, FOO, like FAUX. So basically, the idea is you have a bunch of immutable objects that have all your business logic and no dependencies. And then you have this ring outside that has all the imperative stuff that touches things like networks and disks that fail and are slow and have to be mocked out. But none of those things have any logic, or at a minimum, like a very, very tiny amount of logic. So the great thing about that is it makes unit tests easy because you don't have to mock anything, and it makes integration testing easy because there's only one or a very small number of code paths to test. And that gives you a very clean separation of like, here's the things that are doing the work, and here's the things that are stringing those things together. So let's talk about language. People tend to take for granted just how powerful a tool language can be. Not this guy. So I kind of, latched onto this idea, particularly the way Brett Victor expresses it in the talk, Media for Thinking the Unthinkable. So before the invention of algebraic notation in the 1200s, math was really, really hard to think about because you had to read this to get this. You had to read all these lines and then kind of unpack this concept in your mind. But when algebraic notation was invented, you could just look at it and say, oh, okay, x squared plus 10x, no big deal. So people were trying to use a language to think about math that wasn't a good representation for it. And this idea of representation, I think, is really key because it frames how we think about problems. So my takeaway was basically, oh, okay, so language is a user interface for ideas. That's cool. So I did, combined with my, new learnings about how language works and my growing visceral aversion for declaring variables, I did what took the next logical step that any reasonable person would do and started writing my own programming language. And, as you do, right? That's not weird. So, and then I happened to be, while I was, learning about parsers and lexers and trying to write one, I happened upon this Rich Hickey talk called Simple Made Easy, where he was juxtaposing simple things versus complex things versus easy things, which is like a different thing. But a lot of times what's easy for us is actually very complex, and we have to think harder to find the simple solution. And one of the juxtapositions that he made was syntax is complex and data is simple. I was like, wow, that's really profound, dude. And I thought, if data is better than syntax and language is basically a UI, well, that's all we do all day, right? We have a composition of data structures and a composition of user interfaces and tie them together with some process. That's programming, right? And actually, I want to sidebar real quickly here because there's this idea that I think is really bad that's been going around that programming is not math. Yeah, but to the extent that it's not, it's programming's fault and it's not helping us because math is way freaking easier to reason about. So on that note, so I started thinking about how to represent programming in a different way. And how do you represent that visually? Because we have all these constructs that are so complex. And then I started learning about this library called RxJS, and they have this one cool thing that they do, which is that they represent all of these concepts in one way. So again, with the down here thing, we're so focused on the constructs of programming that we miss kind of the essence, I feel like. If you think about an if block versus a where clause in an SQL query. Completely different constructs doing basically the same thing. They're acting as filters on a set of data. So we end up with this proliferation of different ways to do the same thing. Now, if you're working down here, the fact that those are two different things is fine. They're completely different languages. But if you start thinking about up here, it's like, well, why? I just want a way to model a system. So with all that in mind, let's make it to do app. It's everybody's favorite thing to do. So this particular example comes from a talk by one of the developers of a library called Lambda.js. So this is what we're going to do with this set of tasks. We're going to do this set of tasks and make a program. So this is, again, from his talk, is the imperative code example of those 3 bullet points. You don't have to read the whole thing. It's a lot. But translated into functional programming with a good functional library looks more like that. And it just seems really, really like clean and elegant to me. And by building up its own vocabulary using functional compositions, it can actually represent the things that the program is doing in a way that's fairly close to the list of bullet points. And so we're getting pretty close to like a one-to-one representation here between the plain language requirements and what the code actually does. And that got me really excited, and I wanted to see how far you could take that idea. So we could start by porting it to ES6 and moving a couple things around and taking a few liberties with Lambda's API to make some things implicit. And it's a little bit more clean, a little bit fewer characters and line noise. Or we could just go whole hog and just cheat and just start inventing syntax out of thin air. And then it almost reads exactly like it would in English, just it says exactly what it's going to do. So that looks really interesting. But let's get back to the idea of representations. What if we have a representation that's completely different but makes a lot of sense to me, and I just need to figure out how to make it make sense to the computer? Well, what about something like this? It's a visual way of saying exactly what you want to do. So I thought that idea was pretty interesting. So I tried to make a thing. So design and engineering. This is really where it gets interesting for me. So everything you saw there was a system of just a composition of data structures being rendered in a user interface. And I wrote a little system that can understand that, but obviously it's just data. I can export it to JSON, but I can't really put it into production. But I can generate something that can put it into production. So I have my task list and have my little set of operations here, and those decompose fairly simply to SQL queries and PHP operations and stuff. And so we have a little code generator that works sort of like this, and that's the really simple, naive way of doing it. However, the really cool thing is because you have a system that's described in terms of data structures from end to end, it's a single cohesive thing, you can actually traverse across it and figure out how data is going to be used. Similar to the way like an optimizing compiler like walks an AST. So you can actually generate much more performant code by taking engineering problems and isolating them away from design problems. So let's say like this one, for example, when you're doing development and you're really going fast, at some point you flip over to take an application into production, then you have to do like all the stupid little performance optimizations, like changing all of your select stars to select foobar baz. Well, that's like an individual unit of work that you have to do for every single application. But if we can separate the design of applications and the way they're composed from all of the engineering problems, at least insofar as is possible, we can solve the engineering problems in a more abstract way so that you only have to figure out a strategy for generating select foobar baz once, and then you're done forever. And it's the same with any other kind of engineering or optimization problem. You want to move logic from the client to the server or vice versa. No big deal. It affords this very easy way of shifting boundaries and shifting the way in which your application is run. And there's really, the possibilities for that are really huge. So one reaction I've gotten repeatedly after showing this to people is that, man, you're going to put us all out of work. Not cool. But that's a very zero-sum way of thinking. If you think about the world and everything around us sells ourselves, our communities, the weather, the stock market, the universe itself. It's all systems. And the key to harnessing the power of systems is being able to understand them. And to quote another well-known British philosopher, that's our bag. So yeah, I think this idea that we'll be out of work ever is kind of silly, because we have so many things to do that are so much bigger and better than what we're doing right now that we will never, ever be done. Thank you.